what we have to think is like that. So this is a reinforced concrete system here. Some chloride ion or water and the other sources are coming from the outside into the concrete, and that's why the diffusion coefficient is normally evaluated. But at the same time, if the deterioration takes place in the concrete system, of course, mechanical property, performance, characteristic will be changed. I mean, initially, we have same strength or stiffness like that, but if deteriorated around here, maybe we have some reduction in the strength, and then like that. So to detect, to find the relationships between the mechanical performance and the diffusion change, so we have to know this curve. I mean, because of the deterioration, yes, the mean of deterioration is, of course, chemical and physical characteristics change in the cement composite. And at the same time, as a result, mechanical characteristics of the cement composite is changed. So I don't know the actual relations, but something like that. This origin, and it's going to the somewhere. Maybe this speed between these relationships can be represented by the mass transfer resistance. To find that relationships, what we should do, so let's explain from this the slide. So there is several scale. This is our target structure scale, and this is it's not not good visually, but this is a hydrate, cement hydrate. So nano or micro size scale, and the millimeter and centimeter scale, which represent the concrete. So we have the strength in each step. So we should know the strength of the hydrate, we should know the strength of concrete, and we should know the strength of the reinforced concrete. Of course, this strength related by this strength, and this strength related by this strength, or molecule strength, I don't know. So, and at the same time, when we want to investigate these strengths or characteristics of each system, everything is a system. So for this range, as you know, the chemo and the physical assessment must be adapted. I mean, it's very appropriate method to know the characteristics of this stage. But here, maybe no need to investigation method of the chemophysical assessment to get the strength of the reinforced concrete system. So for this range, the appropriate assessment method is a mechanical assessment. I mean, let's say this is something like the weight of the assessment method. Here, we have a big weight in the chemophysical assessment, and here, the other side, we have to bring we have a big weight in the mechanical assessment. So how we can connect this area and this area? So as one of the idea, yes, of course, as Professor Nakamura has explained about the durability, the mechanics, durability mechanics. Yes. That is the something like another explanation way for this slide. And yes, then based on this understanding, we are now thinking about this story. So our target is here, but to know the actual performance of these members deteriorated by the many kind of the mechanism. So maybe we should start from this mesoscale. So I mean, let's say frankly, we gave up to start from this the nanoscale. So we just decided to start from the mesoscale. I mean, so mesoscale, our mesoscale is the, let's say, 5 millimeter or 1 millimeter or 1 centimeter, something like that. Then using the mechanical characteristics of this level, we probably can explain about the mechanical or the physical characteristics of the semi-macro the level, like a concrete. And using the some analysis or something, maybe we can introduce into the another world, I mean the macro level, to represent the our target. I mean the capacity or ductility of the RC structures members. So this is the what we are thinking about now. So today, I'm talking about the our new approach for this mesoscale level to detect the relationships between the chemo and physical characteristics and mechanical characteristics. So, okay, maybe okay, let's explain this one as well. Okay, what I'm saying now is, so here, this is a mesoscale. I mean, this range, this range. So in this range, we can perform the mechanical test and the chemical test and the physical test to link each other. So, I mean, these chemical properties, physical property can be considered indirectly the influence of the environmental action. And we can relate it to the mechanical properties. Then using RBSM, which is introduced by the Professor Nakamura, using such the discrete method, we can maybe find the mechanical and also the physical characteristics of semi-macro concrete. And then finally, it's very far from this level, but maybe we can introduce into the other the use for the easy way, like FM, to know the mechanical performance of a structured member. This is our methodology. So, yes, RBSM itself is already explained by the Professor Nakamura, and I will explain briefly. The elements are linked using two springs. That's why we need two models for this normal spring and this is shear spring, sorry. This is normal spring and shear spring. So this is our target. I mean, if we can get the rule of the deteriorated concrete of this normal spring and the shear spring, then we can take into account that influences into the RBSM system. So far, we have developed this kind of the macro scale, same macro scale analysis. In fact, this program is developed by the Dr. Nagai, who will present after me. So it can predict this kind of the local failure. And also, the method has been expanded for the fatigue problem. So in fact, it has been developed by the Dr. Matsumoto, who is also today's speaker, and maybe he will explain about the detail of this fatigue simulation. So using that RBSM, so we are now trying to evaluate the mechanical performance of the such mesoscale concrete after the deterioration. So using this several testing, I mean, so first of all, of course, we have to prepare the specimens. Let's say, a typical size is a thickness of 5 millimeter, and length is 70 millimeter and the width is 30 millimeter, something like that. So using this, the mesoscale specimen, we will perform the fractional test. So to detect the tensile strength of the mesoscale level and the Young's modulus and the fracture energy and so on. So after this fracture testing, of course, we have this cracked, and we have two specimens from the one specimen. Then following, we will carry out the shear test to detect the shear strength using this kind of the two-phase, the direct shear test. So this is the mechanical test what we have developed so far to detect the mechanical performance of mesoscale specimen. And also, we have to combine the other testing on the chemo and the physical the observation. So like to detect the calcium hydrate, amount of hydrate, we will introduce the TG-DTA thermal analysis to get the CH, and also to detect the amount of the CSH. So we are now currently applying the methanol acetic method and so on. And also, after the deterioration, some new products, some new the hydrate or components would be generated. That's why we have to check what kind of the precipitate would be developed or not. So using the X-ray diffractometer. And also, at the end of this kind of the testing, we are now doing the pore size distribution. Maybe some of you know about her, using the Mercure instruction technique. So these are what we are doing as mesoscale chemo-physical testing. By combining all informations coming from the mechanical test and the chemical test and the physical test, we are now trying to develop the rules for the RBSM simulation. So this is, in fact, the ongoing research. I mean, using the idea, we are now thinking about doing the freezing thawing test and calcium rating and chemical attack and fatigue underwater. I mean, if the concrete under the water, not only the mechanical action, but also the chemical and physical action would be introduced in the concrete system. That's why we are now introducing our technique into this problem. And at the end of the ongoing research, we just started the fire attack. So in fact, we are now detecting the amount of CH and the CHS after the fire attack. And in fact, last week, we got the first results. What we have surprised is after the 60 minutes or 120 minutes, so completely no CH and no CSH. And that's why we have very small strength. So anyway, this is what we are doing. Just started what we are doing research on the current approach. But today, as an example, I would like to explain about some fundamental results in the calcium leaching approach. So using maybe the 10 slides or something, I will explain what kind of result will be currently has been collected. So okay, in this test, so we did perform the immersion test into the liquid. After the immersion test, we did apply the bending test. And after the bending test, we did the FA analysis to detect the tension softening curve, the back analysis to find the resting modulus and tensile strength and fracture energy. And at the same time, using same specimen, we applied the chemical analysis to know the amount of CH and CSH then finally, we try to find the relationship between the two informations. So this is a situation of the immersion test. So in this example, the sodium chloride and the calcium chloride were adopted as the deterioration source. So after the 1 month and 2 and 3 and 6 months, the immersion, we did this friction test. And of course, before this kind of the observation, we have checked the influence of the size of the specimen and the influence of the size of the fine aggregate. So, of course, the low displacement curve are different from the different size, but the local response, I mean, the softening curve doesn't affect so much for in the range of the size of the fine aggregates. Okay, this is the result. So it's not good, the visual. So, but yes, after the some months, the surface situation, the condition was the change, of course, and then this is the change of the CH and CHH. So here, the result for the sodium chloride, and this is the result for the calcium chloride. So tendency is the same. This is a red shows the amount of CH, and blue shows the CSH. So the CH is quickly disappeared, but the CHH is reduced gradually like that. But the tendency itself is does not change so much. But yes, the amount itself is really reduced after the immersion. And then this is a result of the friction test. This is a stress, and so this should be K, displacement. So for the reference, and 1 month, 2 months, 3 months, and 6 months. So yes, you can see here very big reduction in the strength for the both of the sodium chloride and the calcium chloride. And after that, using the back analysis, we can detect the tension softening curve for the each solution. Then of course, this tension softening, I mean the friction energy, is really changed because of the deterioration of the rigid. And this is change of the tensile strength with time. As I said, the hydrate, amount of hydrate was changed, and also the strength was changed. So now we can connect the two informations. You can see here. Okay. Sorry, I forgot to put the figure which shows the represent the relationship between the mechanical characteristics and the chemical components. But the okay. Please allow me to explain about this slide. So as you maybe understood, the strength could be changed, and the height rate was also changed. So that's why maybe we can connect each other based on the amount of height rate change. The one idea is maybe poor structure was changed because the amount of height rate changed. But at this moment, we could not check the pore size distribution and the pore size itself. That's why we just introduced the amount of the height rate of the CH and CSH. So using this kind of equation, we just find the uh,